Okay, cool. Hi everyone. This is the second live stream that we're doing. We're going to be looking at the Math of Motion series. I've been working on a few videos that are sort of breaking down what we can do with vectors and how we might find that useful. And I'm finding that I'm spending a lot of time on it, and I'm working on some tools for visualizing things, and I'm starting to I guess I'm wanting to make sure that what I'm creating is what people are interested in. So what I figure I'll do is I'll live stream what I'm working on and what I'm explaining, and then if anyone has any questions or any particular things about vectors they're trying to figure out, they can ask in the chat, something like that. So I've got a lot of I don't know what you call it, I guess formulas and different techniques for finding out different things about vectors that I'd like to go over. And I just want to show you a bit about the state of the whole thing and what I'm hoping to achieve in this live stream. I'm just gonna go ahead and jump on this very early days website I've been working on. It's just a couple of tools because sometimes it can be really helpful to have something to play around with to learn more about it. It's just going to open this up, www.piratesjustr.com, and then we'll just go into, I think it's projects, okay, vectors, okay. So this is the sort of thing we've been working on. So this one at the moment is saying if you've got a line and you've got a point, then what's the closest, this purple one here, oh wait, you can't see that, okay, that purple one there, that's the closest point on that line. So this sort of thing, we're just learning how to work this stuff out and where it might be useful. Okay, so I've got a bunch of examples. This one's showing like a delta position, like how far from pretty much the vector from the pink to the yellow one. And yeah, so what I'm hoping to do is I'm hoping to go over a few of the particular formulas, and also maybe tweak this website a bit. You can see it's fairly there's a few things missing, and I'd like to have a bit more information going on and that sort of thing. So yeah, we'll get started. I'll start by doing a bit of an explanation of some of the basics. Oh no, okay, before I do that, I'm just going to do a quick little overview of what we'll be looking at. That might be the best thing. Okay, so let's go to line graph. Okay, so the first thing we're going to go over, just like in our one-dimensional vectors, was just like the basics. So we'll just say the math of motion. Oh no, if my pen doesn't work, the math of motion. Okay, so the first thing we'll do is the basics. This is really things just like magnitude of a vector, the distance between two vectors. Maybe quickly just look at some of the simple things like how to add two vectors together or scale a vector. We'll also look at speed. You know, how quickly say you have a mouse like tracking how quickly it's moving across the screen. Okay, then we're going to look at some things like how to find if you have a vector going this way, how to find a perpendicular, a vector that's at a right angle to it. So we'll just go perpendicular. I would like to briefly just cover some of the real basics of trigonometry. Trigonometry, of course, we'll look at radians as well, the difference between radians and degrees. We're also going to do a fair bit of stuff with angles. Okay, so there's a lot of things we can do with angles, and I guess it depends what you're wanting to work out. But we're going to look at some of the building blocks, some of the stuff that we can work with angles on. So I'm just gonna put angles as one of the topics, and The next thing we're going to look at is, you know, because we often think of vectors as like an x and y position. Sometimes it's useful to think of them as like an equation form. For example, sometimes you'll talk about a vector as having a slope and a y-intercept. You know, so there's just different ways of, I guess, different ways of describing a line, and where that could come in handy. Some of the stuff I'm really interested in doing as well is, I guess it's something like prediction or yeah, motion detection and prediction. I'll just write that motion maybe, or motion understanding, sure. Okay. So that's for example that we're gonna look at. Let's say you're assuming that someone's trying to move in a circle, or that someone's, you know, moving more or less in a circle, and you want to understand what that circle would look like, where the center of it would be, and yeah, what the radius would be, etc. So yeah, so we're going to look at that sort of stuff as well. Okay, so I'm going to go ahead and get started with just the really simple stuff. We're going to start off with really simple, the magnitude formula, and that's something that is rooted in Pythagoras stuff. It's Pythagoras came up with this. He came up with this really interesting, I don't know what you call it, really interesting visualization of how to find, if this is a magnitude here. Sometimes we call it the hypotenuse. So I'll put a little h there. Is how to find that hypotenuse, and he's come up with this formula. It goes like this. It goes c squared equals a squared plus b squared. And what he's saying is, what he sort of, I don't know how he sort of came to this conclusion or discovered this. He says that if you have a square that's 4 by 4 and a square that's 2 by 2, like this, so that's 2, that's 2, that's 4, that's 4, then this square here, so if we're drawing a square off each of our lines, hopefully you can see that. So this is our triangle, and we're trying to find this hypotenuse. Then he's saying that this square here, this top square, this c squared, is equal to, you could fit this one and this one exactly inside this one. So we can use that formula to find out exactly the length of the hypotenuse. So how we can do that is we can go ahead and write, so if we know c squared is a squared plus b squared, well then we know what, so we'll call this one a, this one b. So we can say 4 squared, basically a squared would be 4 squared, right? So c squared equals a squared plus b squared. We go 4 squared plus, hi John. How you doing? Yeah, okay, so we're going with 4 squared plus 2 squared, essentially. And so that's going to be our c squared. So all we need to do to find this c, or the hypotenuse, is we just need to get the square root of 4 squared plus 2 squared. So all we need to do is to go c equals the square root of 4 squared, which would be 16. 16 plus 2, which would be 18. The square root of 18. I don't know my square roots very well, so I'll go ahead and Google this one. Let's see. We just go square root of 18. Okay, 4.2. So now that we've sort of figured out that our hypotenuse equals 4.24. Alrighty, that's magnitude. Okay, and so the other thing I'm wanting to do in these videos is, because this is a sort of the math, and sometimes you can get a lot of resources on the internet that are like, oh, okay, this is the mathematical formula to figure something out, and it doesn't necessarily translate it to code, which is what we're sort of working with. So what I'd like to do is do this example, and then, oh wait, you can't see that. Damn, whoops. Okay, sorry, I was writing there and I forgot that I hadn't put this up. Okay, see that? Yeah, okay, so yeah, c equals 16, the square root of 16 plus 2, that equals 4.24. All right. What was I saying? Okay, yeah, so I'd love to do some code examples. So let's jump into the code and get started with that. Okay. Hopefully these code examples will be they'll be fairly, I want to say, like language agnostic. Like, it doesn't really matter if you're going to be putting this in Unity or Unreal or just on the web. Hopefully, just if you can see sort of a code translation, it should be fairly easy to translate that into any particular language. Okay. Okay, so this is the project that I was working on that I showed at the beginning. If you just sort of come in, I'll show you it again. This is a very new website. I'm sort of working on these I guess vector examples. You can go on these right now, even though I'll be editing them and maybe even updating the website as we go. So yeah, so these are a few examples, and so we've already got a magnitude example. Beautiful. So what I've got here is I've got the frame rate really slowed down, and this little line here is showing the magnitude of the vector. And you'll notice that whether I'm going left or right, it doesn't matter, because this is just telling us how long that line is. So let's have a look at what that looks like in the code. This is I'm using an environment called processing, or P5. It's kind of like how do you describe it? It's a layer on top of the web canvas, which sort of makes it really easy to work with. Okay, so where is it? Magnitude. So this is essentially in any particular frame, then this code will run, and I think at the moment it's running at 3 frames per second. Fairly slowly, so that you can sort of see the changes. Let's see. What I'll do is I'll go ahead and I'll open this up in the live what do you call it, hot reload, so that you can see as I make a change what it sort of does on the screen. Okay, so I'll just go to, let's see, npm start. I think that's right. Oh, npm start. Okay. So, pop this over here. And I'm just going to set at the moment it's opening a delta position as the default example. I'm just going to set the default example to our magnitude example, which should be in UI. Okay. State equals magnitude. All right. So now we've got that magnitude example going, and if I go back to this, which is essentially this entire function is what would run in a frame, and there's 3 of them per second. And we've got this vector2 helper function, which sort of contains all the nully math that we can have a look into. So just for an example of what we can do, if I wanted to also display the position of the vector, or the so just display the position of the vector. I'll just go position. Let's see, x and y. So I'm just passing in the values of the position, and now you can see we're able to see the position as we go. One thing that I've noticed one thing that this example is doing, which I'm going to change in a sec, is this is calculating the magnitude of the delta position, as in this is saying, okay, so I was here and now I'm here. Now what's the distance there? So this example really should be called distance rather than magnitude. I'm going to go ahead and change that now. And we'll make another example which is simpler. Okay. So that one can be distance and this one can be magnitude. So I'm just going to simplify this a bit. So we don't need the delta position. Instead, so we're just going to take the magnitude of the position, and then we're just going to do a line from the center of the screen to that position. 0 to 0. Yeah, if you have any questions about how anything in particular, I don't know how in depth to go here, like whether to talk exactly about what's going on, how the examples are working, or whether to just stick to the math. But yeah, feel free to ask any questions if you have one. Okay, so now we've got our position of our x and y. I'm just going to go ahead and remove all the decimal places. Okay. So now we've got our vector, where you'll notice that no matter which direction it's pointing in, we're getting this magnitude as it's always going to be an absolute value. The length of something is always going to be a positive value. So let's see if I can do this. One of the most famous magnitude examples is what they call the 3-4-5. 3-4-5. What is it? The 3-4-5 triangle. Because let's see, if I go back to the drawing board, as it were, the magnitude of 3-4-5. Oh, sorry, something's just got to draw. There's no point explaining it. Okay, so if you have a length of an x value of 3 and a y value of 4, like this. You can say 3. You remember we're doing our square, so 3 squared equals 9. 4 squared equals 16. 4 squared equals 16. 9 plus 16. So remember, c squared equals c squared. Whoops. C squared equals a squared plus b squared equals, let's say, 9 plus 16 equals 25, and 25 we can easily get the square root of. Sort of like, yeah, it's much easier to work out. So c equals 5, right? Okay, so that's why this example is famous, 3-4-5, because you can work it out in your head, the 3-4-5 triangle. And it's a good way to test whether your formulas are working. If you're able to figure out an answer and then compare it to what you've written in your formula, it's much easier to work with. Okay, so if I set x to, let's see, if I set x to 30 and y to, I don't know if I'll be able to get exact enough, y to 40, then the magnitude is about 50. Okay, so yeah, it's looking close enough. Maybe I've set x to 300 and y to 400. Can I do that? Y to 4, yeah, okay, there we go. That's a bit easier. Okay, so yeah, if x is about 300, y is about 400, then the magnitude is about 500. Okay, I'm just going to show you the math behind it. In our Vector2 helper class, you can see there's quite a few functions. We're just going to focus on the simple ones. And here's our formula. So really, the magnitude just being the square root of x times x and plus y times y, which is, yeah, x times x being x squared. And that's pretty much magnitude. Now we're going to look at direction. Let's see. Where's the good old... Okay, here we go. Direction, okay. Okay, direction. Direction is, if you're talking about a direction vector, or at least if you're talking about you have a position vector, which is we describe a point in space. Generally, when we talk about a direction vector, it really just means a normalized vector, which means a direction. I'll just write this down. Direction vector that's the same as saying a normalized or a unit vector, which means it has a magnitude of 1. So any vector that would be have a magnitude of somewhere inside here. That's a unit vector. That's a unit vector. That's a unit vector, etc. So when we talk about getting a direction vector or normalizing a vector, is another way people often say it. We're really saying take this vector and give it a length of 1. So how do we do that? There's a couple of ways we can do it. One of the simplest ways is, especially now that we've worked out our magnitude, is we can scale our x and our y by that magnitude. So let's see if I can sort of explain this. So there's our x and our y. What we want to do, unit vector. What we want to do is we want to say, well, if we know that we're gonna set the how do I explain this? I'll write out the formula, then we'll have a look at it. Okay. So the formula equals let's say direction vector, or we'll say how do I write this? Or normalize. Okay. So a shorthand for writing a let's say, oh no, that's not right. Okay. So the formula is if you have your x value, so you say let's say we just call it a normal vector, normalized equals x. The x component of that vector will be the original x out of the magnitude. So let's say we have that 3, 4, 5 triangle again. So x being 3, y being 4. And if our magnitude is 5, then the x component of a normalized vector would be 3 out of 5. So that's 3, that's 4. So in other words, it equals x out of magnitude, and the y component equals y out of magnitude. In other words, we'll take this 3, and to find our unit vector, I'll just draw it down here. Then this would be 3 out of 5, and the y component would be 4 out of 5. Okay, so we sort of scale it by the magnitude. And let's have a look at how that sort of works in code. Let's see, where's the example? Okay, so I got this direction example. And again, this is it's called direction, but it's really the delta direction. It's the change in direction from one point to another on the screen. I'd like to just start with regular old direction. So what I'll do is I'll change this name to delta direction. And let's go ahead and have a look at our direction script. Oops. Alrighty, let's see. I'm just gonna set the default display to the direction now as well. So let's go direction. Okay, and now we're just gonna change. Let's see this direction script. All right. So I'm essentially just gonna simplify what's already here. Okay, what happened here? Okay. So I'm just going to remove this stuff instead of this direction AB. I'm just going to set this to a direction. Normalize the pos. Okay. So hopefully just by doing this, we're gonna end up with some really nice examples that you can sort of go on the website and play around with. By the time this stream's ended, a few things might have changed. It might look a bit cleaner. So yeah, so same as the last example. What I'm gonna do is I'm just gonna do a line from 0. Let's see. Okay, we'll do 2 lines. We'll do a line from the center of the screen to the actual position, then a line from the center showing the normalized vector or the direction vector. Okay, so I'm just going to simplify this a bit. Okay, so we'll go from 0 to the position, and also a line from 0 to the direction. We're just going to need because the direction is a unit vector, which means the x and y component at the very most will be 1. We won't be able to see it because that'll mean 1 pixel in this program. So what I'm going to do is I'm going to multiply it by 100. 0.y times 100. Okay, beautiful. I'm just going to set that frame rate to update all the time. So what's happening here? Pos A. Okay. So this is saying, it's saying, oh, because remember we're changing it from when it was like a delta direction, how much the directions changed. I'm just removing all these old values. Okay, still asking pos B. Can't see it. Oh yeah, it's just at the end there. Alright, so now we've got a vector where no matter how long the vector is, we're always going to get this grey one will always have a value of 1. And you can see this information coming out here. It's saying, okay, yep, so if we've got a line that's exactly just going to the right, then the direction will be exactly 1 on the x and 0 on the y. Same if it's going up, it'll be 1 on the y, and if it's going in between, it'll be somewhere in between for both of them. We're going to use this concept of directional normalization a lot in the future. Okay, that's direction. Now let's look at delta position. And for looking at delta position, again, I'm not sure exactly like what level to sort of start talking about these vectors on. So what I'm going to do is I'm going to quickly go over some of the real fundamentals of vectors, and that's just some of the really simple math that we can do with them. Let's see. So let's say we have a oh yeah, and no, it is worth going over because there's also some really great ways of visualizing the simple math that we might be using all the time. Like for example, let's say we got add and subtract, and also we'll do add, subtract, and scale. They're the 3 that I'll really just look at. Okay, so we have, let's say we have a vector that is, let's say, I don't know, it's here. We've got a vector going here, and we've got another vector that's, say, going, I don't know, down here. Okay, so we've got our 2 vectors, and let's say we want to add them together. Well, to add 2 vectors, we simply just combine the x components and combine the y ones. So we say, I don't know, let's say v1 plus v2 is another way of saying that is also saying, oh, whoops. Oh, I accidentally did the undo. Okay, v1 plus v2 equals, let's say we just say v1 dot x plus v2 dot x and v1 dot y plus v2 dot y. All right, so it's sort of the same way. Yeah, that's two different ways of saying the same thing. A really nice way of visualizing it is if this is v1 and this is v2, you can literally draw v2 at the tip, from the tip of v1, draw v2, and that will give you your answer. It's a really nice way of sort of looking at it, you know, and we can work it out. So if v1 dot x, so write this out. Oh no, I'll just show it out. Okay, so the x component of v1 is 4, and the x component of v2 is 1. Well, 4 plus 1 is 5, so that's worked out. Now, if the x component of 1 is the y component of 1 is 3, and the y component of the second one is -2. Well, 3 plus -2, or 3 minus 2, is 1. So yeah, so we got that answer. Let's go ahead and see how we can do that in the code. Oh, before we do, I'll just quickly look at the other two. So we've got add. We also want to look at subtraction and scale. Subtraction is just the opposite of adding. So in other words, if you have a vector that's going, let's say here, and a vector that's going maybe, I don't know, in this direction, let's say a vector that's going here, well, to subtract one vector from another, we just move from the tip of vector v1, and this is v2, move from the tip of v1 in the opposite direction of v2. And, you know, we can work that out. So, let's see, if I might as well write it down. So, v1 minus v2 equals v1 dot x minus v2 dot x, and also v1 dot y minus v2 dot y. All right. Yeah, and again, we can work it out in our head to make sure that we're getting it right. Hello. Inaslejo. Tell me if I'm getting that right. Inaslejo. Okay. If we've got our vector 1 at 3 on the x, and our vector 2 is -1 on the -1 on the x, then we simply subtract. You know, so we could say 3 minus -1 is 3 plus 1, right? So 3 minus -1 equals 3 plus 1. The negative values subtract each other. I mean, cancel each other out. Okay, so we get that the number 4. And the same with with the y value, we just say 3 minus 2. 2 on the y value, 2 on the y for v1, and 2 on the y for v2. 2 minus 2 equals 0. And so yeah, so that's how we work out our subtraction. Now scale is a little bit different because we want to do two things when we're scaling a vector. The first thing we want to do is we want to normalize it, and then we want to multiply it by the scale value. Okay, so let's say we have a vector that's, say, here, and we want to scale it by 3. What that means is we want to give it a length, this is the length or the magnitude. We'll just go magnitude. We want to give it a magnitude of 3. Something like that. Okay, so how we do that is, first of all, we give it a magnitude of 1. So we say we normalize it. We already looked at how to do that. So we just say normalized v normal equals let's see, the x component is the we'll just call this vector v1 dot v1 dot x out of magnitude. I'm glad to hear that. Glad to hear I got that right. Inus Leo. Inus Leo. And the y component is v2. Oh, sorry. Y component is v1 dot y out of the magnitude. Okay, so that's how we can find our normal value, and then we'll just say v scaled is going to equal simply the x equals v normal. Oh, it's just getting messy. I'll be right. Okay, the x is v normal dot x multiplied by the scale. Oh, that is getting messy. Okay, so essentially what we do is I'm really bad at writing what do you call it, shorthand mathematical notation, because I write in code most often. So I'm really bad at writing this stuff out. But essentially, scaled equals normal or normalized vector times the.
Website c-bone.com. They say the SI joint is stabilized by a network of ligaments and muscles, which also limit motion. The normal sacroiliac joint
Sorry, guys.
has a small amount of normal motion of approximately 2 to 4 millimeters of movement in any direction.
My Google Home's
So yes,
talking to me.
a little. To read more, look for the link in your Google Home app.
Sorry, guys. I'm just I might turn down Google Home. Oh, I have no idea what that was about. All right. Anyway, so essentially, once we normalize the vector, then we multiply it by that scale. So let's go ahead and now have a look at how we do those things in the code. Okay, so let's see. I'm gonna first of all, I'm trying to think whether I should write examples for this stuff, because this is about as simple as vectors can get. I'm trying to think whether I should have a little tool to play with them. It is a nice thing to visualize. What do you reckon? Oh. Might as well. And then you can also see a bit of the process of how I'm sort of writing these examples. Okay, so let's go ahead and create an example for adding. Let's call it add.js. And I've got, essentially, I'll show you a little bit about how this app's working. If we've got our index.js, so this is where the project starts, we're sort of doing a bit of setup up here, a little bit of setup, and then we're creating a sketch, or essentially creating a canvas. We're using P5 to do so. And then we're gonna this is a loop function, essentially, this draw function. So every frame it'll loop over and do this one. It's clearing the background. It's moving to the center of the screen. It's flipping the y-axis. This is a scale. It's flipping the y-axis, and it's setting the color of the pen, essentially, to black. It's drawing these x and y sort of coordinate lines, setting the frame rate to 60, and it's getting the position of the mouse relative to the center of the screen. And then we're figuring out which button has been pressed. So every time you press a button, then it's going to change this ui.navigator.state, and then it's going to run the loop for whichever example has been selected. So let's go ahead and add one in. So we've got it's the add example. I'll make this one example for adding, subtracting, and scaling. I'll just make it the one. So we'll just call it vector math. I think that'll be fine. Okay, so where was I? I'm going to go back into my index. So we'll create a new one called a new case. We'll call this one vector math. So by a new case, I mean there'll be a new button which will be called vector math. When you click on it, it'll run the vector math loop. Okay, and yeah, I'll just add in the import of our vector math file. Okay, vector math. Okay, and also I'm just in the UI. I'm going to add the button that we can press. Okay, so vector math. Just gonna make sure I spelled that right in the index. Oh no, I haven't updated it. Okay. Okay. So when that vector math button's pressed, then it's gonna take us to this vector math page, which, as you can see, isn't doing anything at the moment. So let's make it do something. So we'll have a function called update. In fact, yeah, I'm just gonna remember there's a few things passed in here. Okay, so one of the things that we pass in is the position of the mouse. The other thing that we pass in is this p. This p is short for our p5 class, which is essentially that's the class that does all the drawing. And UI, that's the class that's going to allow us to write in this little info box. Okay, so I'm just gonna, let's see, what I'll do is I'll have a really simple example next to the one I'm gonna write, which will have, like, you know, how we did it last time. Let's see, direction is a pretty simple example. Okay, so we've got our, oh yeah, so another way of writing this function, because it's being imported by our index file, we just say module.exports equals position, our p class, and the UI class. And now, a really simple example, we can just say UI.info, which is the info element, the info text element, and we're just going to say .body.inner text equals, and we can write whatever we want here, hello world. Oh, hello world. Whoops. Hello world. All right. So now that's sort of the basics of how this thing's working. Now let's go ahead and do our add. Okay. So if we have our vector would be our pos. Let's just draw an ellipse wherever the position of the mouse is. Okay. So we just say p.ellipse pos.x pos.y. That's the position of the ellipse, and we'll just say 20 by 20. All right. So now we've got our ellipse. Maybe we want it to be a different color, so I'll just say p.fill. This is setting the fill color. Maybe I want to set that fill color to maybe light yellow. So we'll just say maybe 255, 255, 128. So that's red, green, and blue. Okay, so now we've got this nice yellow color for our mouse. What else do we want to do? Maybe I also want to draw a line. Line to the vector. So I'll just go p.line, line 0, 0, 0 to pos.x, pos.y. All right. So now we've got our vector. Let's create I'm wondering how to do this. We'll just create a second vector which will be fixed, right? And then we'll see what it looks like to add them together. Okay, so I'm just gonna say what I really should do is I'll take this pos. I'm just gonna call this pos B. This will be the second position because we'll have another one which will be called pos A, and it'll have an x value of, I don't know, 200 and a y value of 300. Okay, now let's go ahead and draw that vector as well. maybe we want it to be a different color. Maybe I'll make it a nice cyan color. Okay, 128. Okay, why didn't that work? So we got our pos B, got our pos A. Oh, maybe it is working. It's just off the screen. Instead of being 300 and 200, I'll make the y-axis maybe 100 and the x-axis maybe 80. There we go. Okay, so we've got that position A, we've got our position B. I'm going to do a line to position A and B. Now you notice that the line's being drawn in front of the circle. I'd kind of like it to be behind it. So all I need to do there is just draw the lines before the ellipses. Pos A and pos A. Okay. All right. So now we've got a vector going to A and a vector going to B. Now let's have a look at, let's do a pos C, which will be the A plus B. Okay, so let's see, we'll just go const pos C equals vec2. Oh yeah, I got to import our vector because I've got this vector helper class. This is sort of how I decided to design this group of examples, because some of these examples rely on the math from the other ones, and instead of redoing things, I've just got this one massive vector2 helper class with all these little functions inside it. I'm just going to go ahead and include it. Const vec2 equals require dot slash vector2, and let's go ahead and look inside at what we got in there. Okay, so there's three functions that we're really interested in, and that's adding, subtracting, and scaling. Now I've just realized that scale is a bit of a it's a bit dodgy, because this is assuming. Remember, we've got to normalize a vector before we multiply it by this s value or the scale value. So I might want to normalize it first and then scale it. So I'll do that. I'll do that now. I'm trying to think if I'll break anything. I won't break anything by doing it, because it should be not. Yeah. Yeah. Okay. This is a better way of doing it. Okay. Const vec. Or maybe that's. I'm trying to think what the standard is. I'm trying to think, because when you're writing like a function that everyone's used to working a certain way, you want it to work in the same way. And I'm trying to remember if, like, for example, in Unity or in even in P5, when they have a vector dot scale, if they mean normalize it and then scale it, or just scale it straight away, like, you know, with any vector. I'm going to quickly look that up. Let's find out. Let's see. I'll look up Unity. They got really good documentation. Unity scale vector. Although they won't even have a function, because they just say times equal. Oh no, they do have a function. Here we go. Okay. So I'm imagining that they won't normalize it first. Let's see. Multiplies two vectors component wise. Oh no. That's something else entirely. Oh no. That's not what I was talking about. This is combining. This is saying. Oh, this is not it at all. Okay, this is more like it. Yeah. Okay, so this is. No, this isn't it. Oh, this isn't it. Okay, I'm gonna try another library, see if it'll help us out. So you go to 3JS. Because this, when Unity says scale a vector, it means combine two vectors, where I mean multiply one vector by one number, you know, so the x by that number and the y by that number. Let's see, I'll just go to documentation of 3JS and just go to vector. Let's see, vector. We'll just go vector 2. There should be a function called scale, hopefully. Scale, PRS, scale. There isn't. Oh no. Gosh. Alright. Alright, maybe this isn't I thought this would be a really standard function that everyone would be using. Apparently not. That's alright. We'll just keep it as it is. We'll just say, okay, if you're scaling a vector, does not normalize first. We'll do that manually. So I'll go ahead and I'll show you our normalize function as well. Where's our normalize function? Let's see, normalize. Oh, this is called, direction. Okay, direction normalize. Okay, here we go. Okay, so this is our other function that we'll be interested in. So we've got add, subtract, scale, and normalize. We'll be using all 4 of these. And of course, normalize relies on magnitude. I'll just quickly, out of interest, I'll quickly show you magnitude as well. Okay, so these 5 functions, because to scale a vector, as in to set a vector with a length of 500 to a vector with a length of 200, you got to, first of all, you got to normalize that vector, set it to a length of 1, and to normalize that vector, you need to find out the magnitude or what the magnitude is. Okay, well, yeah, and that sort of things we already sort of quickly looked at in the stream. All right. So now what I'm going to do is I'm just going to visualize what this would look like, and how I'm going to do that is we've got our vector A, which is the blue one, and our vector B, which is the yellow one, and I'll just add a vector. I'll just call it I don't know, added vector, and I'm just going to add it to the end of B, so we can sort of visualize what that looks like. So what I'll do, and this is our add function, simple as return a.x plus b.x and a.y plus b.y. Alright, so here's our vector math class, and let's see. Oh yeah, so instead of pos c, I'm going to call that, let's call it added pos, added vec equals vec2 dot add pos a pos b. Alrighty, and now let's go ahead and visualize that. So I'll do another vector, do another ellipse. Why not? Okay, added vec dot x and added vec dot y, and I'll change the color to, I don't know, red. All right. So now we notice that we've got this vector A and we've got this vector B, and the added one is sort of A plus B. I'll also do a line I'll do a line from pos B to the added vector. Added vec. Okay, so now we've got this sort of A plus B. You might be able to imagine, and I'm not sure whether I should do it or not. I will do it. I've also got the subtracted vec. Now the only difference between the added and the subtracted is the added one, it doesn't matter which you do first, whereas the subtracted one, it does. So for example, const sub vec equals vec2 dot sub pos, let's say pos b pos a. Okay, so that means b minus a. And let's do a line of you'll see why in a sec. I'll just do an ellipse. An ellipse to the subvec dot x and subvec dot y. Make this an ellipse. All right, and we'll make the subtracted one. No, I really want to make the added one. Added one should be blue, and the subtracted one should be red. Yeah, that makes more sense. 0, 255, and the subtracted one is 255. Okay. Give the ellipse a width and height of 20. Okay, so you'll notice that because we subtracted, we went pos B minus pos A. Remember, you'd go to the top of pos B and go in the opposite direction of pos A. Whereas if I swap this around, pos A minus pos B, well then it's going to be off of pos A. It's going to go to the end of pos A and then go in the opposite direction of pos B. It's the other way around. So that's something just to keep in mind when working with vectors. Yeah, I'm not sure why they're... I don't know why they're both red. Why are they both red? Huh. Oh, that's the added one. Okay, so yeah, so the red one's added one. Oh, I know why. Okay. Okay, there we go. Now our added one's blue and our subtracted one is red. That's much less confusing. Alright. Okay, so I'm just going to make the subtracted one B minus A. So this would be our position, and then we're subtracting A from B. Yeah, and the last thing I want to do is just have a look at scaled. I'll draw a line as well from the subtracted vec to pos B as well. And then we'll have a look at scale. Alright, so there's our added and subtracted. And scaled works a little bit differently. So first of all we got to look at our normalized vector. So const normalized vec equals vec2 dot normalize pos B. And first of all we'll visualize that. So I'll go ahead and we'll just draw a line. Just draw a line from pos B to the normalized vec. The only thing I'm going to do is remember, because the normalized vec has a length of 1, which in the case of pixels we'll barely be able to see, so I'll multiply that by 100. Multiply vec dot x times 100, and normalize vec dot y times 100. All right, and also I'm going to change what we call the stroke weight. P dot stroke weight. This is how fat the line is. So we want to sort of be able to see the difference. Oh yeah, and I'll make it from the center, not from pos B. That makes more sense. 0 on the x and 0 on the y. Okay, so now we can see we've got this sort of normalized vector, which we already had a look at. What we're going to do a bit different here is now we're going to scale it by, say, let's say we want it to be, at the moment it's got a length of, I don't know, probably about 300. Maybe we want to give it a length of 50. So how we can do that is we can just use that scale function. So const scale vec equals vec2 dot scale normalize vec. Remember that we got to normalize it before we multiply it by this value. Normalize vec by 50. Okay, and now we'll just do a line to the scaled vec. No, I did that wrong. What was that? Oh no, I did that right. Yeah, that's it. Okay, yeah, so I'm just going to remove the normalized vector line, and then we can see that now we've got a vector that's got a length of 50. And yeah, that's the basics. Let me know. I'd love to hear whether you guys think we should go straight on to the advanced stuff, or there's a few more little things I'd love to go over just before we go into the... I'm hoping that this is sort of going to give us a strong foundation to build on when we start getting into some of the more interesting stuff. But yeah, it's always good to sort of have a good foundation. Next thing we're going to look at is delta position. In fact, we've kind of already looked at it, but we're going to think about it in a slightly different way. So at the moment, we're sort of looking at the subtraction as in you have two vectors and you're taking one away from the other. When we're talking about delta position, it's more talking about you have something that's moving and you want to find out how much it's changed. It's essentially just subtracting one from the other, but you're sort of thinking about it a little bit differently. So let's have a look at, might as well, yeah, I'll quickly show you what it looks like on the good old graph. Okay. So, let's say we have let's say we have what's a good example? You're playing like a magic game, and you're in VR, and you got your wand, and you're tracking where the wand's moving in space, and you want to know the direction that the thing's moving in. Well, let's say all right. First of all, let's look at what information we have. We have the information of its position in every frame. You'll say like, what's the controller's position? What's the controller's position? And you get, let's say you got two of them. You got frame 1, it's here. Frame 2, it's here. You want to know this vector between 1 and 2. So that's pretty much what we're looking at. So let's say we have a position A and position, I don't know, in a frame it moves all the way over here. This is position B. Now you want to know, now the direction's important, you want to know the direction from A to B. And I think I did this in the one-dimensional example. A really nice way, if you're ever confused, is to reduce the dimensions, if you can ever do that. So for example, sometimes I can't remember, it's like, is it, to get the delta position, is it A minus B or B minus A? Then I just think of one dimension. And this is like, I really find this helpful. So I often use one dimension and really simple numbers that I can work with. So let's just say, let's simplify it and only use the X values. Alright, so let's say we have a position A. No, I'll do it even simpler. We'll have position A and position B. Okay, so we want to know the direction of A to B. So we know it's going to be a positive number because A is 3 and B is 5. So we can figure out, oh, okay, well it's probably, it's probably B minus A. It's probably direction equals B minus A. Oh no, it's not direction, rather it's delta. Direction's different because direction is a normalized vector of our delta position. So first of all, with this little triangle, it's often how delta position is written. Delta position equals B minus A, where A is the first point and B is the second point. Okay. Yeah. Okay. So that's our B minus A, and then we can obviously subtract A from B. 5 minus 3 is 2, and so now we know our delta position equals 2. All right, and we do the same thing as just as we were looking at with our subtraction of vectors. We can say if we've got a vector A is here, vector B is here, we've got A and B. We can say, well, delta position, delta pos, well, that can equal, let's say, equals B minus A. And if A is, let's say, might as well work it out, do a bit of math. Okay, so we can say A is 4, B is 1 on the X. So we say, so 1 minus 4 is the X value. And the Y value is, let's say, 4 minus 2. 4 minus 2. 4. Whoops. 4 minus 2. Okay, so that's going to equal, the X value will be 1 minus 4 is, did I do this right? Yeah. 1 minus 4 is, Oh yeah, it is right. It is right, because we are moving. I was like, 1 minus 4 is a negative value, but we are moving in the negative direction. Okay, so 1 minus 4 is negative 3. Okay, x is equal to x negative 3, and y is 4 minus 2 is 2. Okay, so we're moving up, we're moving negative 3 in the x-axis and negative 3 in the x-axis and positive 2 in the y-axis. So this delta position vector would actually be something like, well, I'll tell you exactly what, it'd be exactly like this position here. So it'd be like this. Yeah, that's our direction. That's our big direction vector. Okay, or our, did I say direction? Delta position. Our direction vector, out of interest, would be the normalized version. So it would be the same as the delta position, but with a length of 1. And we'll use both of those a lot in the future. Alrighty, so that's that. What's next? Oh yeah, I'll quick. I think I might have already done this example, but I'll just show you what it looks like in the code. It's always nice to have that translation. Let's see. Direction. Oh no, no, we're not looking at direction. I keep saying that. Delta position. We're looking at delta position, the change in position. So remember, as I was saying, as something's moving through space, it's essentially the A would be the magenta and B would be the yellow, and it's saying what's the B minus the A? What's the direction from A to B? And you'll notice if it's really big, if I move it really fast, it'll be a big vector. If I move really slow, it would be a small vector. And you can use that to tell what direction you're moving in. Okay, so that's something we use a lot. Let's see, distance. Have I done distance yet? Oh, okay, so I've added distance here. I've added distance. Well, I mean, I don't know. I don't know if I should really go into this, because distance is just the magnitude of a delta position, right? So if this is our delta position, then we've already looked at magnitude, which is how long a vector is. And you can say, well, the distance is just the magnitude of this delta position vector. What I'll do, I won't make another example. What I'll do is I'll just add this information to our little info box here. So I'll delete this distance example. It's not necessary. And oh no. Wait a minute. Wait, was I meant to, distance? No, because yeah, we do still have our magnitude. Okay, so, excuse me. Okay, so now we're going to have a look at our, in our delta position example, we're just going to add a little bit of information here which will tell us the distance between the two vectors. Okay, so delta position, at the moment we're just saying our x and y position. Okay, so now, so yeah, so I haven't shown you in the code yet. So our delta position is really subtracting pos and last pos. I don't like these names. I'm going to rename them. I'm rename last pos to pos A, as in the initial position, and pos B will be the next position. Let's see if I can do this for just the pos B. Pos B. Okay, pos B. Pos B. Alright, so from pos A to pos B, so I'm just going to update all these. Strange, it's drawing the ellipses twice, don't need to do that. Okay. Okay, pos is not defined. Okay, pos A equals pos B. Delta position. Okay. Okay, and now I'm just going to add the information for the distance between two vectors. Okay, so we'll just say distance. I'm going to calculate it by just saying const dist equals the vec2 dot magnitude of the delta position, and we'll just pop it in there. Okay, oh yeah, I'm just going to do it, make it a whole number as well. Just round it off. Okay, so yeah, so the distance is just going to tell us really how quickly, or not how quickly yet, just the distance between two vectors. The reason why we don't say it's how quickly something's moving is because it's a measure of distance, not you know, speed is distance over time, and this is just distance. If you had a really slow computer that was going exactly 1 frame per second every frame, then you know distance over time would equal the distance. But we're gonna figure out we're gonna work it out more cleanly. Yeah, and to do that, we're gonna look at something that's pretty cool. I think it's pretty cool. It's called a delta time. Something that, you know, if you ever done like game development or graphics, or a lot of computer cases use delta time. What's the amount of time between two things? And it's funny, we've just looked at delta position, because delta time you can really think of as yeah, and you just sort of if you wait, I'll just do this example. Delta time is just it's a similar. You can think of delta time as similar to delta position, as in you have your time at frame A and your time at frame B, and the delta time equals B minus A. Okay, so 6 minus 2, our delta time. If this was in seconds, then our delta time would equal 4. The reason why we need delta time is to work out the speed of a vector. So let's say we've got our delta position. We know how far it's moved, but we don't know how quickly it's moved. To work out how quickly it's moved, we need to know how far it moved in a certain amount of time. So let's have a look at a few examples. Okay, so you have your really simple vector. Let's say you have your pos A and your pos B. Let's say you can visualize what this vector is going to look like. This time I'm not going to do the math. Instead, I'm going to visualize it, which is just simply saying distance from A to B. Well, I can see that's 2 on the x and -1 on the y. So this is our delta position. Okay, so we just say delta pos equals 2 and -1. Okay, so now let's take a few examples. Let's say that we've got a computer that's running at frame per second. If our speed equals dist over time, you know, let's say if this is in pixels and our time is in seconds, it would be pixels over seconds. You'd say pixels per second. Okay, so let's say if our time is equal to 1, then I don't know where I'll write this here. Okay, time. We'll just do a time and speed. If our time is equal to 1, then our speed would just be the magnitude of this vector, right? So yeah, I don't know if I should. Okay, so you know what? No, let's work it out. It'll be good practice. Let's work out our magnitude. So magnitude is equal to the square root of x squared plus y squared. Okay, so in other words, magnitude is equal to the square root of 2 squared plus -1 squared. So let's punch that into Google. Square root of 2 times 2 plus -1 times -1. Now that -1 will cancel itself out. We're always going to get a positive value for our distance. Okay, so that's our distance. So our distance here, or our magnitude, is 2.2. Okay, that's quite a good number to work with as well. So if we've got our speed as distance over time, 2.2 out of 1 would be 2.2. Right, divided by 1 is 2.2. Okay, so if I've got our time between frames is 1, then our distance would just be 2.2 pixels per second. Let's say we've got a delta time of 0.5. So if our delta time is 0.5, which means there's 2 frames per second, right? Because it takes half a second for each frame. Then our speed would be 2.2 out of 0.5, which means in half a second we move 2.2 meters, which means in a second we would move more than that, right? We'd move 4.4 meters, 4.4 or pixels or whatever your scale is. Okay. If time is 0.5, we move 4.4. Now, usually delta time would be quite a low number. Like for example, let's see, if we had 10 frames per second, delta time would be 0.1. Let's see, I wonder if I could do it. If it was 50 frames per second, 0.02, I'm gonna guess, something like that. So yeah, so the lower the delta time, the more the speed is magnitude, multiplied by, or the higher the speed, in other words, because you can imagine if you say you've moved this far in this frame, if it took ages for you to move that far, then your speed's quite slow. But if the delta time is really small and you move that far, then your speed's much faster. Okay, I hope that's making sense. So what I'm going to do is I'm going to show you the code example for this one. All right. So I've already got the example going, and you can see we're moving at we've got a delta time of 0.3, which out of interest, delta time and frames per second, they're the inverse of each other, which means if your frames per second is it's 1 over whatever the other one is. So if your frames per second is 10, then your delta time would be 1 out of 10. If your frames per second is 100, yeah, anyway, you get it. So our frames per second is 3, and so our delta time is about 0.3. Now our speed is our magnitude multiplied by our delta time. Our magnitude. It's our magnitude out of delta time. So our speed is because our delta time is less than 1. Anything out of a number that's less than 1 is kind of like it's multiplied. It gets bigger. So our speed's bigger than our magnitude. If I went into that example, let's have a look. If I went into that speed example, and I'm wondering. Okay, so what I'll quickly do is I'll just quickly show you what if the frame rate was like 0.5. 0.5 frames. Is that right? Oh, I don't think I can do that. I don't think I can do less than 1 frame per... Oh, no, wait, no, I've gone to the wrong example. Okay. So, it takes... What's it? 0.5 frames per second. So it takes 2 seconds for each frame. So now, our speed is kind of half of our magnitude. It's really slow. Anyway, so that's sort of a bit of a feel for how that works. I'm wondering if I should go into how delta time is sort of calculated. It's kind of the same as delta position. I think you sort of get it, right? If you have your current time, then you simply just say you simply keep track of your last time, and then your delta time is your current time minus your last time, and then I just divide it by 1,000 to convert it from milliseconds into seconds. Yeah. And then your speed is your magnitude out of delta time. And that's kind of how that one's calculated. All right. So, if you made it this far, congratulations. That's the basics. That's the sort of the, I don't know, I want to call it like, if computer graphics 101 sort of stuff. Congratulations. Now we're gonna look at some things that are a little bit more, I want to say like exotic, a bit more interesting, and we can do a lot more stuff with them. Next one I want to look at is what we call a perpendicular line. Really simply, if we have a line that looks like, let's say it looks like this, and we want to get a line that looks like this, and we can say that there is a right angle between them. How do we work that out? Well, let's just try something here. What would happen if I just flipped the x and the y axes, right? What if I flip the x and y axes? So let's say this is v1. So let's say v1 equals x is 3 and y is 2, right? Okay, so what happens if I flip that? What happens if I said v2 equals set the x to 2 and the y to 3? Well, then the x would be here and the y would be here. That's not quite what we're after. So that's not quite what we're after. What we want is we want to flip, we want to invert, we want to set it the x to the negative y value. In other words, so because that's not quite it, notice how it's kind of like the mirror image of the one we were looking for. It's kind of like a way of working backwards for solving a vector problem. What we're going to do is we're just going to say, what if the x, let's say, let's just call it perp equals x negative v1 dot y, and the y is simply the x value, the non-inverted, y is the v1 dot x. Then you'll notice that we get this perpendicular vector. Okay, so we flip the y-axis. So we say the x value of the perpendicular vector is the negative y value of our original one. So in other words, in our original one it's 2, so it's going to be negative 2. Yeah, our x-axis is going to be the negative 2 of the y-axis. So here we are, we've moved negative 2 on the x-axis. And then the y-axis, well, that was... okay, so what was 3 on the x-axis is now 3 on the y-axis, which gives us, which would take us up there. And there is our new vector, our perpendicular vector. Yeah, that's fairly straightforward. I'll just quickly show you that one in the code. I'm not sure I've written an example for it yet. Let's see, perpendicular. Okay, yeah, so we've got one thing I did do is often when we're talking about a perpendicular vector, we're really talking about the direction, like the perpendicular direction, if you want to find the normal of a vector or this sort of thing. So what I did here is normalized it first and then set the perpendicular. Let's have a look at the example. Okay, so we've got our vector A, and then we've got our vector, our new vector, which is perpendicular, and I just added it to the end so you can sort of see the relationship between them a little bit more clearly. Like I could, for example, I won't do it. You sort of get it, right? So we're essentially saying this is our vector A, is the yellow one, and then the one that's perpendicular is our cyan one. I'll quickly show you the math behind it. In our vector 2 class, we've got let's see, perpendicular. Okay, yeah. So we've got our original x. We're going to take x is going to equal the negative y, and y is equal to simply the x value of our original vector. Okay, that's perpendicular. Now, now we're gonna take a step back, because our next stage is where things start to get a little bit more interesting. Oh, that's a good stretch. On a sec. Oh. All right. Our next stage is the angles. Angles. That's what we're looking at next. Okay. So angles. First of all, we're going to look at simply the angle. The angle. Oh. Yeah. Okay. So what we're going to do is a bit of a warm up. Is we're going to look at a thing called polar coordinates, because we're going to do some introduction stuff to trigonometry. And we're going to look at polar coordinates, which is a really nice way of working with it, and then we're going to look at angles, and then we're going to look at the angle between vectors and the nuances in that. Okay. First thing I want to talk about is something called radians. Radians. So, you know how we got like okay, see how my knowledge goes. You know how we have we have units of measurement, right? We have kilometers and we have miles. Sometimes we want to use kilometers, sometimes we want to use miles. Well, the same goes with angles. The most famous example of angles is degrees. I almost wrote on my iPad with a whiteboard marker. Where's the pen at? Okay, so the most popular unit of angle measurement is degrees. Have a circle like this. We go like 0, let's see, 90, 90, 180, 270, and 360 is all the way around. That's your degrees. Now, interesting thing about degrees, a little fun fact is, to the best, I'll just say to the best of my knowledge, yes, there are only 4 people watching. I'm not sure if those amount of people watching includes myself. So and then so like now there's 4, now there's 3, now there's 4, now there's 3. I don't know. Okay, so something interesting about degrees is they're not as I don't know, like you might wonder, like, where's this 360 come from? It's not really it's to the best of my knowledge, it's not really got a great reason. I believe it was I was reading somewhere that the Babylonians were the first one to start using this number 360, and that's because they had a base 60 unit of measurement. Oh, sorry, base 60. They had a base 60 math system, right? We've got a base 10, which means once you get to 9, you add a number to the end and go again. 0, 1, 2, 3, 4, etc. A base 60 would be like count all the way to 59, and then you've got your 10, that sort of thing. That sort of idea, anyway. So that's sort of, you know, because 60 goes and 360 go really well together, right? 60, and out of interest, 60. If we looked at I'm digressing a bit here. That's all right. It's a live stream. If you have a circle and you were to divide that 360 into values of 60, then you start to get these really nice thirds. You sort of get the points of a hexagon. Thirds, sixths. Maybe they had a base 6 system. That makes sense. I think that makes sense. Yeah. Okay. So if it was a base 6 system, then let's see if I'm gonna get this right. So, yeah. Okay. So 60 degrees. 60 degrees would be about here, and then you'd have 120. Am I getting this right? Yeah. 60, 120. But then 120 plus 60 is 180. Oh, that is right. Yeah. Okay. Yeah. No, I'm just figuring this out. It's kind of interesting. I guess I'm working backwards from why the Babylonians figured that 60 was a great idea. If they're only working with hexagons rather than, or I guess they could work with squares as well. You know, square being 0, 90, 180, 270, 360. Well, if we're working in hexagons, then we'd have 0, would say 60 would be about here, 120 would be about here, 180 would be about here, 240 would be about here, and 300 would be about there. Okay, and then so you've got this sort of shape of a hexagon. I don't know, maybe they worked with hexagons more or something. Anyway, that's sort of got to do with degree. That's degrees. That's the cool stuff about degrees, is it goes into divides in 4 really well, divides in 6 really well. So sometimes you want to do that. It's really easy to visualize. You know, I can say 180. You instantly know I'm talking like a semicircle. Oh, I'm glad you like the portal project. You know, I had this idea of, I don't know if I should say, you know, when you're thinking back on a project and it's like, oh, well, this worked really well, that worked not so well. I've got some ideas for the portal project that I haven't tested out at all. Because you know, like the flickering was a real issue, and like I've seen other people having a go at doing it. They're also finding that problem. I was thinking if you had 2 portals. So you had a portal that you step through, and now you're like this in between where you wouldn't have to instantly change between portals. You could sort of do it step by step. Maybe that would be better. I'm not sure yet. Like almost like a portal tunnel. But I haven't played around with that at all. It's just an idea. Anyway. Okay, so we were talking about degrees, and now we're going to talk about radians. So that's degrees. Now radians. Radians is a bit different. It's the way it came up. Way that sort of folks started working with it is a little bit different, because it's actually got to do with a circle itself. You know, you might notice that a radian sounds a lot like radius. Well, out of interest, we notice this circle has a radius of 4, and that means that a radian for this circle literally is 4. Oh no, I got to be careful how I describe this. No, a radian isn't literally 4, but the distance of a radian is 4. Distance of a radian. Okay, so a radian is a description of distance around the circumference of a circle. Okay, radians and circumference of a circle. That's what it's really got to do with. So, for example, 1 radian in any circle is about here. I'm going to say about there. Yeah, it's around about there. And in this circle, it turns out that 1 radian would be 4. So the distance, if I was to walk along here, that would be 4. If it was a circle, if it was say one of these little circles, then the distance would be 1, right? Okay, so this is 1 radian. Let's figure out what happens if we keep adding radians. Okay, so we go, okay, 1 radian, 2 radians would be about here, 3 radians would be about here, 4 radians would be about here, 5 radians would be about there, and 6 radians would be about there. Now you'll notice that it doesn't quite add up to 6 radians. It is, out of interest. You might, I don't know if you sort of figure, like putting this together, but you'll notice that this is 3, this is 2, this is 1, right? Now, yeah, so I know I'm confusing you by saying the distance of a radian is 4. I won't say that. A radian is 1 when it's about there. Oh, okay, I'll make that clearer. Okay, now you notice this 3. Well, that's really, it sounds a lot like pi, right? So pi equals 3.14. You notice at 180 degrees, well, that looks like it's spot on pi, and it is. Now, remembering that this formula, the circumference of a circle. Come back to the idea of the portal. Yeah, you know what I might do? What would be fun, because I'm really enjoying just doing a live stream and mucking around with it. So I might do one at some point. See if we can. We'll call it Portal 2. Why not? It's not a bad idea. Yeah, I was watching this video. Who was it by? Code Parade. Wait, okay, I know I'm completely digressing. I don't care. Okay, yeah. Yeah, this awesome video. This guy was, you know, this idea of non-Euclidean geometry is in like, it's like not really. It's not really the same as portals. It's kind of saying, well, if you go in a room that's got, I'll just show you. It's awesome. Non-Euclidean geometry, Code Parade. Okay, yeah. So this is really cool. Some examples of what this guy was doing is okay, yeah. So he's got this room where he's walking through it, and I'm not sure. This one of the rooms only had 3. It was, you know, he keeps walking around. I think this one's got 6 rooms, but it looks like just a regular room. Let's see if we'll do that again. Hold on a sec. Okay, wait, we'll do this first one. It's like really cool stuff. So non-Euclidean geometry, and it doesn't really make normal sense. So this is a house that's only got 3 rooms to go all the way around. If that makes sense. You don't really pick up on it until you watch it a few times. But yeah, I'd love to get back into that stuff. Anyway, so he did all that stuff with portals. He did say that he tried to do it in Unity and couldn't really get it happening. He said he had to make his own what do you call it, graphics engine. So hopefully we'll be able to do it just with Unity, but we'll see how we go. All right. Anyway, digressing. Okay, so we're back to radians. And we're talking about pi, and we're also talking about the circumference of a circle. This is how I love to think. Let's clear our heads a bit. I love to think about radians as this rule that we use a lot for circumference of a circle equals 2 times pi times r. Now let's just pretend that our circle has a radius of 1, which means we don't need to worry about that r. That means the circumference of the circle is 2 pi. Well, guess what? If you were to describe an angle in radians as 2 pi, that is all the way around. So I'm hoping this is sort of starting to come together. You know, so for example, if you said radians equals pi equals pi, well, that's the same as saying equals 180 degrees. It's the same thing. So why do we even care about radians? Why do we want to use them? Okay, so if we're gonna go into trigonometry and a whole bunch of other stuff with angles, then the language of computers, because it's got such a close tie to the actual geometry of a circle and the geometry of angles, rather than degrees, it's much more popular to be used with math libraries. And so that's the language we'll sort of be sticking with, unless we're just sort of offhandedly describing an angle, you know, roughly 90 degrees is a nice way of saying it, rather than, for example, to describe an angle of 270 degrees, often you would say 3 over 2 times pi, which is a bit of a mouthful, you know. So that's essentially if this is pi over 2. This is down here, 3 over 2 times pi is equal to pi plus pi over 2. It's kind of the same thing. But yeah, it's a bit difficult to speak in radians. That's why we often just speak in degrees. Okay, so that's kind of the basics of radians. I don't really have an example. Oh, I could do an example. Should I do an example? I will do an example when we're looking at angles. When we do an angle example, I'll punch in the radians and the degrees. We'll do a little conversion between them. The next thing I want to talk about is trigonometry. And trigonometry is like, what's trigonometry like? It's the math of angles. If you ever want to like talk about the relationship between a triangle and its angles, or a triangle and its sides and its angle, then you're most likely going to be working with trigonometry. Okay, so we're going to look at how are we going to work this out? Okay, first I'm going to quickly go over the formulas, and then we'll look at implementing them. Okay, so so there's three formulas that are like the, I don't know what you call it, the Bible of trigonometry. You're just always coming back to them, rearranging them, reusing them, inverting them. These three formulas we use a lot, and there's a little, I can never remember the word for this. Not an anecdote, a shortening. I don't know what you call it. An expression we use to remember it, and that's the expression is so ka toa. Okay, and these are sort of like a little. Oh gosh, how do we describe this? These are just little ways of remembering the order of these formulas. I'm gonna go ahead and give you an example, and then we'll have a look at how to figure it out. Okay, let's say we have an angle. We have a hypotenuse of the angle, which is always the longest side of. We have a triangle. We have a hypotenuse, which is always the longest side of the triangle. We have an angle, and the triangle in all of our examples will have a right angle. It's always a right angle triangle. These rules only apply to triangles with right angles. With one right angle. Okay, so we have our angle, we have our hypotenuse. Now, in the world of trigonometry, we also got to describe our other two sides discretely. And how we do that is we say this is our opposite side of the angle. Okay, so that's the opposite. And the adjacent side, the side that's next to the angle, is called adjacent. Okay, so if the angle was up here, then those roles would be reversed. That's sort of how we figure that out. Okay, I'll see ya, Inos, Leo. Good night. Okay, so once we have this adjacent and these opposite sides, then we can start asking questions and saying things like, I know the hypotenuse of my angle, and I know the angle. I keep saying that. I know the hypotenuse of my triangle, and I know the angle, and I want to find out the length of this opposite side. How do I do that? Well, this is where trigonometry says, I know how you do that. Here we have our so formula, which if I were to write it out, it looks a little bit like this. It says sine of theta. Theta is short. This little character here. That's another term for an angle. Okay, so we say sine theta equals the length of hypotenuse. No, it doesn't. I lied. So this is where the expression really helps. Okay, so sine theta equals this little O is short for opposite. The length of the opposite over the length of the hypotenuse. Okay, so this is where so comes in. Sine theta, that's the S in so, equals opposite O over H hypotenuse. So. And so. And so, we use this formula to work out our length of our opposite side. So how do we do that? Well, let's say we've got a hypotenuse of, oh beautiful, this is a 3, 4, 5 triangle. That was a mistake. So a 3, 4, 5 triangle, it simply means that if you've got one side being 4 and one side being 3, then the hypotenuse will be 5. Okay, so let's pretend we didn't know. Let's pretend we don't know that this length is 3. That this sorry, I've got to be more explicit. We don't know that the length of our y-axis is 3, and we're trying to work that out. So how we do that is we say what do we say? We say sine theta equals equals O over H. Well, we know that sine theta equals, let's see, our O over 5, because we know our H is 5. So that's also going to equal, let's see, what do we say? We say sine theta times 5, sine theta times 5 is going to equal our opposite. I've just realized that because I don't know the length of our angle, it's going to be a little bit difficult to work this out. Just please excuse me. I'm just going to find out this, because we're working with an example here. I'm just going to find out what this angle is secretly, and then we'll be able to work with it, and we'll be able to find out this length of the opposite. So just bear with me here. 8, 10, 2, 3, 4. Okay. Okay. I think I've got the answer. We'll see if this works. Okay, so I've been told by the computer that this angle is 1.2. So in theory, if we go 1.2, in theory we can say this. We can say O equals sine of 1.2 times 5. Okay, so let's go ahead and work that out. So if we go sine 1.2 times 5. Oh, this example is going horribly. That's not the answer. That's not the answer, because we know the answer is 3. I think that's because it's not 1.2 radians. I've gotten that wrong. I don't know how to work this out without a calculator. Okay, I think the problem here is I've presumed to know what this angle O is, and I've just confused everyone by doing that. So what I'll do is I'll clear this out, and we'll just start. I'll start that one again. Okay, so we're working with this SOHCAHTOA group of formulas, and we're going to look at this first one. Sine theta equals O over H, equals the length of the opposite over the length of the hypotenuse, right? And let's just say we have some triangle, and we know that this angle of the triangle is I don't know, equals 1.5 radians. Okay, that sounds good. Okay, so we know that the length of this one is this angle is 1.5 radians, and we know that the length of our, let's just say, our hypotenuse is equal to, I don't know, 4. Okay, hypotenuse equals 4. Well then, with this formula, we can rearrange this formula to find out, and this is because this is the side that's opposite our angle. We know that this is our opposite side, and we're trying to figure out what the length of this opposite side is. Well, if sine theta equals O over H, if we multiply both sides of this equation by H, we can say sine theta times H equals O, right? Sine theta times H equals O. And that's not a 0, that's the opposite, equals opposite. Okay, so if we've got 1.5 radians and our length of the hypotenuse is 4, let's go ahead and work that out. So we said sine of 1.5 times 4. Okay, and now we've got our answer, 3.98. Okay, so now we've figured out that the length of our Opposite side is 3.98. So that's essentially our sine formula. Now let's have a look at the other two. Yeah, we'll go ahead and look at the other two. Okay, so we've got our sine, so, ka, toa. Now this next one is, this formula, we can write this out as this. It says cosine of theta equals adjacent over hypotenuse. What's the adjacent? Well, the adjacent is simply if we have a triangle that looks like this, the right angle there, and some angle that we know there, then if this is the hypotenuse, which is always the longest side, and this is the opposite, and this, well then, okay, this is the side that's opposite the angle, then this is the side that's adjacent to the angle, next to the angle. Okay, so that's how we find out which side is our adjacent, and then we use the same technique for finding out the length of our adjacent side. So let's do another example. Let's say theta equals, I don't know, equals 2, and our hypotenuse equals 4, 3, why not? Hypotenuse equals 3, then we can go ahead and work that out. So we say cosine theta equals adjacent over hypotenuse. We could also say, once we multiply both sides by the hypotenuse, we say cosine theta, cos just being short for cosine, cosine theta times h equals adjacent, right? So cosine of 2 times 3. Let's write that in. Cosine of 2 times 3. Okay. Now, yeah, oh, cool. Cool, okay. Okay, this is cool that this happened. So, we remember, this is interesting. Remember we're working in radians. Just going to jump back to our example. So you notice this is a negative number, negative 1.2. Okay, so our length equals negative 1.2. Now you might notice that if this adjacent, if that's an x value of a vector, then that means that our triangle looks something like this. It goes in this direction. Because if it's the x value is negative, then it's going to go that way. This is because our theta, our angle, is greater than half of pi. Remembering that radians go from where are we? Radians go from well, I'll just do a quick little circle down here. Radians go from 0 to pi to 2 pi is all the way around. This is pi over 2, about 1.6. So 2 as a value is somewhere like this, right? So when we say an angle of 2, when we say an angle of 2, we're really describing an angle that looks like this in radians. Okay, and then we use our trigonometry functions to essentially work out on the x value, this x value, and this y value. I hope that's sort of clear enough. Okay. So yeah, so I'm hoping this is sort of starting to come together. This is so we've worked out sine and cosine. Last one, which is comes in very handy, is our tan function. In a way, the tan function is a little bit easier to sort of to explain because if we've got let's say a vector here. Oh no, it's not a good example. Let's say we've got a vector here, and we know that it has an x value of 4 and a y value of 2, right? Let's see, I'll just write out so ka toa again. So ka toa. We know that our x value x value equals 4 and our y value equals 2. Let's say, for example, where we want to find out this angle. This is the most common application of the tan, well, no, I don't know if it's the most, it's a very common application of the tan function. Let's say, for example, let's say, for example, you're driving a car, or you're not driving a car. Let's say you're in VR and you've got controllers that are simulating the driving of a car, and the steering wheel's here, and you're moving your hand around the steering wheel. Well, you sort of want to know the angle between your hand, which you're just getting as a position, and that central angle position. And so you know the x and y values, and you want to get that angle. So how we do that is, I'm just going to write out our tan formula. Tangent of theta, tan theta equals O opposite over adjacent. Remember, our opposite is our y value, and our adjacent, this would be an opposite and this would be our adjacent. Opposite and adjacent. Okay, so now that's our formula that we work with. We're about to do something really interesting that we do need to do every now and then. And this is called inverting our trigonometric, inverting our trigonometry function, you get it. Essentially what we want to do is, because we're after theta, we want to do this. We say tan minus 1 of the opposite over the adjacent equals theta. Okay, so that's how we sort of write that. This is the inverse of the tan function. It's a different function. We pass in the opposite over the adjacent. And then that's pretty much how in fact we can work this out. Except there's a little gotcha, and I'm not sure if this is sort of gonna. It probably will work with this example, but it won't always work, and I'll show you what I mean by that in a sec. So let's go ahead and punch this in. So our opposite is y, and our adjacent is x. So we'll say the inverse of tan minus 1 of y over x equals theta, right? So we go ahead and punch this in. So we say a tan is another way of writing tan minus 1, the inverse of tan, of what was it? 2 over 4, and this will give us our angle, 0.4 radians. And if we were to, sometimes it's really helpful to check our answers, see if it's making sense. We know that 90 degrees is pi over 2, which is about 1.6. 1.6 is here. So if we divide that by 2, we know our 45 degrees is pi over 4, otherwise known as 0.8. So we know that it should be less than 0.8. And what was our answer? Our answer was 0.4. So yeah, no, our answer does look good. It does look correct. It's just that it doesn't always work. And I want to show you, I don't know if I should show you, but we should just take my word for it. But if for example, let's say these were negative values. Let's say this is an opposite direction. Let's say this goes this way. Okay, so we got our tangent function. Let's say we got -2 and -4. Well, let's go ahead and calculate that. What is that? So 2 out of 4. 2 out of 4, right? Our last one was 0.5. Okay, that's making sense. But what about our -2 out of -4? Oh, crap. -2 out of -4. What's that? Well, it's also 0.5. In other words, what we've done, the problem is that our tangent function is describing, it thinks that you're talking about the same angle. So there's a little way to go about this in code, And that's our what we call a tan 2. Okay, so there's two tan functions. There's tan, or a tan, and a tan 2. Okay, so in other, just to really quickly sum it up, if you're working with an angle that's between here and here essentially, any of these angles, then a tan will work fine. A tan, which is O over adjacent, just pass in those values, O over A, that'll be fine. Well, but a tan 2, what that does is that accounts for these angles that are going in what they call these, in these areas, in this area and this area here, then our a tan 2 is what we want. In fact, generally, like I've personally never worked with this a tan function. I only ever work with a tan 2 because it'll give me a value that's, it'll work with all the quadrants. And the only difference is, instead of passing in O over A, we pass in O comma A. In other words, in the case of a triangle that looks like this, we pass in the y value, then the x value. And that's how we work with our a tan 2 function. Okay, that's, if you're still watching, awesome. That's trigonometry in a nutshell. Let's have a look at some examples. Let's have a look at some examples. Okay. First example I'd like to look at is polar coordinates. Polar coordinates are a really nice way to sort of get warmed up to vectors. Just thinking, you know what? Before I do, I feel like I should just take a little break. I'm going to take a break for maybe 10 minutes, and then I'll come back and we can pick up where we left off. Let's put a little timer up. All right, I'll be back. Alrighty. Headset, yes. So, where were we? We've just had a quick look at trigonometry. Oh yeah, now we're going to look at polar coordinates, which we've sort of already done. It's just a way of thinking about our trigonometry functions. When we say something like, how do we describe it? Okay, so we've got a vector, right? We talk about vectors, and we're used to saying things like it's got a position of x at 4, and y of 3. That's one way of describing our vector. But it's not the only way of describing our vector. We could also say that it's got a radius. This is equal to saying a radius of, what's a radius? Radius of 5. Radius of 5, because this is a 3, 4, 5 triangle. 3, 4, 5 triangle. It's got a radius of 5 and an angle of well, let's see. You know what? It'd be worth finding out the angle of this. Okay, what is the angle? Well, it's just, I'm digressing a little bit, but this is sort of what I'm getting at here is that there's two different ways of describing. Well, there's many different ways of describing a vector, and this is another way. You could say it's got an x and y position. It's also got a radius and an angle. I'm curious now. I'm going to go ahead. I'm going to look into this. I'm just going to see what this angle is. Let's see. Oh wait, I'll show you how I figure this out. Okay. If we've got, let's see, we know our x and we know our y. We're going for theta. Well, we can probably use the sine function. So sine of theta equals opposite over hypotenuse. Now we're going for theta, so we can also say this. We can invert our sine function. So we can also say sine theta equals sine inverse of sine of O over H. Well, let's work that out. Our opposite, our opposite is 3, and our adjacent is, no, sorry, not our adjacent, our hypotenuse is 5. So, the inverse of the sine of equals sine minus 1 of 3, sine minus 1 of 3 over 5. Let's go ahead and figure that out. A sin 3 over 5. Alrighty, so that's our degrees. 6.64. Okay, so now we know our radians are 0.64. 0.64. And that looks right as well, remembering that 45 degrees in radians is about 0.8. So we know that this angle that makes sense. We can sort of error check as we work. All right, that's looking good. So yeah, so what I'm saying is that polar coordinates are I'm guessing an angle around a pole. I'm guessing that's where the name comes from. If this is our pole, usually the positive x-axis is your pole. It's an angle around a pole and then a radius of how far out it is. And how we work that out, the formula for our polar coordinates, let's say we're going to convert from Cartesian to polar coordinates, x and y being Cartesian. So Cartesian to polar coordinates, I think we just worked it out. So essentially we have our let's see, our 3, 4, 5 triangle. Okay, first of all, you need to figure out your magnitude, which would be, this is the magnitude of your vector, which is also the radius, or the radius of your polar coordinates. So Cartesian, we could probably say like something like cart to polar equals, so the magnitude, so we say radius is the, we've already looked at magnitude, so we'll just say magnitude of our vector. I'll just say vec vec, and the angle, or theta, you could use either the sine or the cosine function. We're just going to use the sine one. So the theta equals sine minus 1 of, in this case, if that's your angle, this is opposite, this is a magnitude, or the hypotenuse. There's so many names to describe the same thing. So this line here is either your magnitude, your radius, or your hypotenuse, depending on who you're asking. We're going to call it the hypotenuse in this point, and that's going to mean sine, the inverse of, to find our angle is the inverse of the sine of O over h, in other words our opposite over our hypotenuse, which is also this magnitude. So it would be simply equals O over h, and our theta will equal sine minus 1 of 3 over the magnitude. Okay, so that's how you figure out your Cartesian to polar. Now we can also go the other way. Let's say we know our angle. We know our angle from the last example. We know it's about 0.6. We know our magnitude. In this example, we know that it's 5. So theta equals 0.6, mag equals 5. Let's say we wanted to find our x and our y coordinates. Well, we use those same trigonometry functions to do that. How we do that is we say, well, we know that this is our opposite and this is our adjacent. Let's say we want to find out, let's say we just write polar to Cartesian. Okay, so how we work the polar to Cartesian out is we say polar to Cartesian is the x-axis is the, because remembering our trigonometry functions, if our x-axis is the adjacent, this is the adjacent line. That's our cosine function, right? So cos theta, cosine of theta equals adjacent over hypotenuse. All right. So we know our theta, we know our hypotenuse, which means our adjacent is cosine of theta multiplied by our hypotenuse. Okay, in this case, we can work that out. We can say cosine of 0.6 times 0.5. Sorry, it's cosine of 0.6 times 5 because we know our theta and we know our magnitude. So let's write this out. Okay, cosine 0.6 times 5. Okay, 4.1. So I know it's about right, isn't it? It's because I've rounded that 0 point. I've rounded that angle. It's not actually 0.6, 0.6 something. But yeah, so it's a 4 point, about 4 on the x. So that's looking right. And now we do the same for the y, except because we're working with the opposite, we use the sine function, which is sine theta. This is SOH, SOH. Sine theta equals opposite over hypotenuse. So y equals sine theta times hypotenuse, and we can go ahead and work that out. So instead of cosine of 0.6 times 5, it's sine of 0.6 times 5, and 2.8. And that's, again, that's almost right, 2.8. That's about here, right? So go ahead and write that out, equals about 3. So that's our polar and polar coordinates, converting to and from polar coordinates. Let's go ahead and have a look at what this looks like in the code. Let's see. I haven't written an example for this, although I think I do have the math for it somewhere. Okay. Hey, Martin. let's have a look at our example. Where are we at? Gonna go ahead and okay. First of all, I'll show you in the code. I'll show you the math itself. Let's see. I'm gonna move this out of the way. Okay, so we've got our Cartesian to polar and our polar to Cartesian. Out of interest, I've used a different method of working out the angle. I'm gonna, like that does work. I'm just gonna show you I'm gonna show you another way of writing this, the way that we were looking at in the first example. So the other way of writing, in fact, it's probably about the same. Okay, so we say const mag equals magnitude of the vector, and then we're gonna say const theta equals the sine. No, it's the a sine math dot a sin of the. Remember, let's see. So I always write it to work this out. I always write out the formula and then like write it in the comments, so I always remember how I came to a result. So we can say let's say we got so equals sine theta equals sine theta equals the opposite. No. So yeah, equals the opposite over the hypotenuse. Inverting that, that's another way to write this, is a sine. So we can also say theta equals the a sin of the opposite. We'll just write O over H. Okay, so let's figure it out. Remember, our opposite is the y-axis. So we'll just write the vector y over and our hypotenuse is the magnitude of the vector over the magnitude. Okay, so that's another way of writing this out. So we can go ahead and return radius is the magnitude and theta is theta. Okay. So that's that one. That's the math of Cartesian to polar, and polar to Cartesian. When we already know the angle, we know the radius. This is a really popular one for computer graphics. If you want to do like things like drawing like really interesting shapes and curves, then often we write the formula out in polar coordinates and then we plot it onto a computer screen by converting it from polar to Cartesian. Okay, so let's go ahead and create an example of this. What's this example here? I think this example is direction. That's quite a nice simple example. Is it? No, it's not direction. Magnitude. What was that example? Vector math? No. Oh, it is. It's the vector math example. Okay. So I'm wondering which one to copy and paste so that we can create a new example, which will be our polar coordinates. Okay. So I'm gonna go ahead and what was it called? Vector math. Okay. Copy and paste that one, and we'll rename it to polar coordinates. Okie dokie. I'm just going to pretty much delete everything here. Okay. So, if you've just joined, I'm sort of working on this. I'm just working on this this is a little tool that's on the website at the moment, on the Pirates for Sale website, and I'm hoping to tweak it a bit, give it a bit more functionality, make it a little bit cleaner. So that it'll be really nice to sort of work with. So what I'm going to do is I'm just going to clean it up a bit. I'm going to add this new polar coordinates example to our application. And how I do that is I'm just going to go into UI. First of all, create the button for polar coordinates. Just set the default state to polar coordinates. And in our index, make sure that it's included. const polar coordinates equals require polar coordinates, and then in our switch statement, I'll make sure that we'll when we're checking the UI whether or not the button's been clicked. Okay, case polar coordinates. And then we'll do our polar coordinates function. Okay, so that's sort of like just the boilerplate, and I know that's it's just giving us what was originally in this thing. Okay, so I'm just gonna simplify this whole thing a bunch. Okay, so all right, there we go. Now all we got is we just got a line pointing to the mouse. So first of all, let's just go ahead and print out our this vector, this x and y value in polar coordinates. Simple enough. So we'll just say const polar. Zoom in a bit. Const polar equals vec2 dot Cartesian. Cartesian just being regular x and y values. Cartesian to polar. And we'll pass in our pos, and then we'll just go ahead and print that out. So we'll just say radius, and then we'll say polar dot radius, and we'll also get our angle. Okay. Now, oh yeah, I'm gonna do it to fixed. Maybe to 2 decimal places for the angle. Okay, so out of interest, you'll notice that our angle sort of goes, this isn't really the angle of a vector. It's a little bit different because this is really saying the, I want to be able to draw it. Let's see if I can, I can't point to it. I wonder if I can, wait, I'll just bring this over here so I can explain something. So we've got our vector here, right? And our angle is, at the moment, our angle is 0.5. Now this is an angle from this line to this, oh no, almost. Okay, this is an angle from this line to this line, right? If we bring it over here, it's not all the way around that angle, it's just this angle, right? And then if we bring it down here, then it's the angle of, it's this angle, and the same on this side, so it's this angle. So, I guess what I'm saying is that it's our okay. This is I'm just thinking about how this works. This is because I've done this this A sine way of working out the angle. Just trying to think if this is the best way to do it. It's probably not. Because, okay, this is my problem. This is my problem. Remember, the whole point of polar to Cartesian coordinates is it's describing that same vector in another language. Because it's saying these angles are identical. This is negative 0.7, this is negative 0.7. Because they're both describing this angle here, and this one's describing this angle here, the problem is that you won't be able to use that information to say, for example, redraw that same vector. So it's not really correct. I'm just realizing as I've done that, it's a little silly. So how I'm gonna fix this is you'll notice that I had my original. There was an original way of writing this let's see, Cartesian to polar formula, which is using the tan2 function, which we did just look at. That's just that's another trigonometric function, something like that. Another trigonometry function which will give us a value between pi and negative pi, which means that it'll be it'll give us all the way around the circle. Instead of, we call these areas quadrants, right? This would be quadrant 1, 2, and quadrant 3, quadrant 4. at the moment, quadrant 1 and 2 are identical, and quadrant 3 and 4 are identical. So in this case, you would say that this is a formula that works with quadrant 1 and quadrant 4 only. It's a way of saying that it only works with these two because these two will give you the same value. And that's where a tan 2 comes in. So I'm just going to replace what that new formula I added with this original one. Okay. Okay. And now we'll notice we get a value that goes all the way up to pi, and then we come all the way back around, and it goes all the way down to negative pi. Okay. So that's Cartesian to polar. Let's has a good example. I'm wondering if there's a good way of showing polar to Cartesian. What if we had an angle that was sort of an angle that was changing with time? Might look cool. Maybe. Let's see. If we go because at the moment we're getting Cartesian to polar. What if we went polar to Cartesian? Okay, let's go ahead and create a polar function. Create a polar. What do we call it? Polar vector? Polar line, something like that. Okay, so we go set const new polar, or I don't know. Yeah, new polar equals let's say it has a radius of 100, and let's say its angle theta will be p dot frame count times 0.01, something like that. So it's got a slowly changing, an angle that slowly goes up. Okay, so now we can go ahead and create our we'll create a second position based on this, which will essentially just be an angle that keeps going around. Okay, so we'll just say const pos2 equals vec2 dot polar to Cartesian. We'll pass in new polar. Oh no, we'll just pass in new polar dot theta and new polar dot radius. Polar dot theta, new polar dot radius. Okie dokie. And then I'm just going to go ahead and draw that. And also I'm going to print it out. I might print it out as the new position. Okay. New pos 2 and pos 2x and new pos 2y. Okay, we'll just say pos2.x and pos2.y. Just remove that hello world. Okay, it's going a little nuts. I'm just going to put it to fixed. Just remove those float values. Okay, now we can see that sort of changing. I'm also gonna draw an ellipse at each of the points. Let's see. So we say pos.x and pos.y and pos2.x and pos.y. Okie dokie. Also gonna maybe change the color. One can be yellow, one can be cyan. Okay, so we notice we got our first one is going our polar to Cartesian, and our second one is Cartesian to polar. Okay, I'm just going to be a bit more clear about what's going on in the info. Okay, so we just say polar to Cartesian. No, that's the second one. And then the first one is Cartesian to polar. Okay. There we go. So, that's our polar coordinates. Yeah, that's pretty much how that one works. What's next? Angles. Okay. I realized that this this Cartesian to polar formula already uses what we're about to look at. It's kind of funny, but it's just I really should have done this angle one first. We'll go ahead and look at it anyway. Angle. First of all, let's do a quick look at an example. Yeah, this is pretty much what it is. Angle is just the polar coordinates without worrying about the radius, essentially. So it's just the angle. Probably don't need to explain it, although I don't know if I really explained Cartesian to polar before. I think I'll quickly go over it. Won't take long. Let's have a look. Here we go. Okay, yeah. So this wasn't a great way of doing this. This Cartesian to polar, like, that's a way of working it out, but it only works for I know I'm drawing everywhere here. It only works for quadrants. So this is our quadrant 1, 2, 3, 4. This way of working it out only works for quadrants 1 and 4. And it'll give, like, you know, the quadrant. What that means is if you have an angle that's like this. Oh gosh, it's getting messy. Okay, you got 1, 2, 3, 4. If you have an angle that looks like this, it'll give you that. If you have an angle that looks like this, it'll give you that. In other words, yeah. So in other words, it works for these two, but it doesn't work for these two. So to make it work all the way around, this is where we use a tangent function. We use this thing called a tan 2. I think I already covered it. I think I did. Yeah, I did already cover it. That's an angle that it's essentially using that tangent function. We go let's say you go tan of theta equals opposite over adjacent. In other words, it's famously known as TOA, which just means that if we have let's see, we've got a triangle that goes it has an x value of 4 and a y value of 3, and we have an angle here, an hypotenuse here. This is our opposite. This is our opposite. Sorry, I'm just trying to undo that. Okay, there we go. We have a hypotenuse here, and this is our opposite because it's opposite the angle. This is our adjacent because it's adjacent to the angle. So x, or a, it's also known as. What we are working out with our TOA function is we want to find out the angle, right? The angle of this vector. Well, for that we use this, we invert our tan function. So tan theta equals opposite over adjacent. Another way of writing that is theta equals a tan, or the inverse of tan, of our opposite over adjacent. And because that would give us symmetrical results in our different quadrants, in other words, this one would be, let's see, this one would be the same as this one. No, yeah, something like that. Then we've got this function called a tan 2. A tan 2, where we pass in the opposite, then the adjacent, separated by a comma, and that'll give us an angle which goes from 0 to pi in this direction. It'll be 0 here, and to negative pi in this direction. Okay, and I'll just quickly show you what that looks like in the code. If I go to vector 2, angle, it's literally just this. It's a angle is math.atan2 of passing in. Make sure you pass in the y value first and then the x value. This is really common if you want to find out the angle of the, like for example, the angle of the mouse about a certain point. That's what it'll give you. One thing to note is you'll notice how, as I go around it, it'll only give you up to like essentially 180 degrees or negative 180 degrees. You might want to change that. For example, let's see if we can. If I go to my angle, if I said if theta is less than 0, so if it's going from 0 to negative pi, maybe you want to add 2 pi to it, which will give it an angle of from 0 to 2 pi, in other words. Okay, so if theta is less than 0, theta plus equals math dot pi times 2. Okay, whoops, let's jump into angle. Okay, so all that'll, theta's a constant. So just say let theta. So all that'll do is, in our angle example, as we go around, then it'll keep going all the way around. Go from 0 to 2 pi. So depending on what you want to do, I might just add this into the information. So make that a const theta, and I'll just make this a const theta 2. Const theta 2. Let's rewrite this equals if theta is less than 0, then we'll write theta plus pi, 2 pi. Otherwise, theta 2 will equal theta. Okay, so we'll just say angle negative pi to pi, and this second example will be angle of keyboard. This is a gold touch. It's one of the best. See, it's got this I'll just pop it over now. Gold touch. It's got the curve on it means that you know, I think they explain it like if you put your hands by your side and you sort of like bring them up, they're sort of they're facing this way. I think that's sort of how they figure that this bend's really good. But yeah, I use this all the time. I wouldn't really be able to go back. Yeah. Okay, so I'm just going to quickly write. Sorry, I'm digressing. I'll just go quickly write from negative pi to pi. Otherwise, from 0 to 2 pi. I've also seen keyboards that are literally like this, and you got like a mirror so that you can see what keys you're pressing. It's kind of the next level. So imagine, yeah, you cut this in half, and then you put, like if you have a box, you would stick one of the sides on each side of the box. Okay. This didn't work. Oh yeah, theta 2. Okay. Okay, so now you'll notice that we got one of our angles is negative pi to pi, and the other one is 0 to 2 pi. I'm just gonna quickly. I'm just also gonna just do an arc for that second pi as well. Maybe 0 to 100. Can't remember what these values are. Theta 2. Let's see. What if I go 200 here? Oh, that's not it. All right, 200. Okay, cool. Okay, so now we're able to see both the angles, depending on which one you're after. All right. So that's angles. We're getting there. Getting through the list. Yeah, we are getting there. Okay, so now we're gonna have a look at something called the angle between. This is where things get really interesting. First of all, we're going to do what we call the signed angle between. There's two common ways of finding out the angle between two vectors. We'll have a look at both of them. Okay. So I'm going to go ahead and write this out. We'll go signed angle between. Okay, signed angle between. What are we talking about? What do we mean? Okay, so let's say we have a vector that's, say, here, and a vector that's here. Okay, this would be vector A, this would be vector B. Well, maybe we want to know this vector. We want to know what's the difference between vector A and vector B. We want to know this angle. Okay, out of interest, this signed angle between means that if B is this way, if B is counterclockwise, okay, this I've got to be explicit here. This is where we've sort of really got to think about how we're explaining things. So if this is our angle A, or this is our vector A, if B is on, if you're going counterclockwise around vector A, if B is here, then it's going to be a positive value, right? If B is, I'll just quickly draw a few. If B is here, it's a positive value. B is here. Oh shit! Whoops. Excuse me. Excuse my language. Okay. If B is here, then it's also a positive value, until we get to this 180. So this would be 180 degrees is what I mean. As soon as we get to here, oh gosh, I got to think about how I explain these things really well. Okay, so let me start again. Remember, we were just looking at vectors, and we're looking at angles, right? And we have our angle where it would be 0, and it would get to pi, and then it would also, that would be going this way. But if the angle is, say, like here, then it would be negative. This is negative pi, and this would be a negative value. So we got, if an angle is in, remember we've got our quadrants. We've got quadrant 1, 2, 3, 4. So 1 is positive, 2 is positive, 3 is negative, 4 is negative. Okay, now all we're doing with a delta angle is with our angle A, we're just drawing our quadrants like this. So if this is angle A, this is our vector A, then you could imagine there's a quadrant that goes like this, right? It goes like counterclockwise the quadrants go. So we go 1, 2, 3, 4. Then again, 1 is positive, 2 is positive, 3 is negative, 4 is negative. This is just a way of explaining that an angle would go from 0 to 180 degrees or 0 to negative 180 degrees. Okay, and so yeah, so for example, if our vector B was, say, here, then it'll be this angle, which would be a positive angle. Okay, so that's sort of like a bit of a background of what we're sort of working out. Let's have a look at them. We've got our A and our B. Okay, now let's work out how we find out these angles. First of all, let's get the angle of A. Well, we know that theta A equals A tan 2. A tan 2, we know how to get an angle. We go A tan 2 of, that's the y and that's the x, of A dot y, A dot x. Okay, angle B equals A tan 2 of B dot y and B dot x. Okay, so that's our angle B. Theta A and theta B. B dot y, B dot x. Okay, and now so all we're trying to find out. So this is theta B. This is theta A. We're trying to find out this one, right? Well, angle between is very much like delta position, as in all we need to do is say angle, or let's say delta angle. Why not? Delta angle equals theta B minus theta A. Okay. Now that's the essence of it. There's just a few little gotchas, and I'm trying to think what the best way to explain these gotchas. It's essentially. You know what? It's all right. I think I'm just going to skip the explanation and just show you the formula. We want to make sure that our angle is our delta angle is in a range. We sort of looked at how it works, how to work out an angle. How to wrap an angle between 0 and 2 pi. It's kind of like that. What we got to say is if our delta angle is greater than pi, then we got to say delta angle minus equals 2 pi. And if it's less than negative pi, then delta angle will add 2 pi to it. Okay, hope that sort of I'm hoping that sort of would make a little bit of sense. What we're saying is, if you end up because of the nature of these delta angles wrapping around, right? If you end up with a value that's accidentally, I'm just going to rewrite this. If you end up with let's say A and let's say B, if you end up with a value that's accidentally wrapping around this way, well, when we're talking about angle between, we're really talking about the shortest possible angle between. So what this does is it says, no, we're not talking about that one, we're talking about this one. That's the essence of why we make those if statements. Okay, so let me show you what that looks like in the code. I feel like my pencil's about to run out of battery. I'm just gonna charge it up. Alrighty, where are we? Okay, signed angle between. Oh yeah, and so just to reiterate, signed angle between means it'll tell you either negative or positive. And yeah, we'll just leave it at that for now. Okie dokie. Where's our math? We'll start off with the math. Signed angle between is signed angle between. I'll just search for it. Signed angle between. Okay. Signed angle between. Okay. Here we go. That should really be. I found that it should really be next to the angle between. I'll just go ahead and move that. Signed angle. Okay. I'll just go ahead and move that up. Okay. So we know how to get our angle. We've looked at the angle formula. So we figure out the angle of A, figure out the angle of B, figure out B minus A, and again, if it's returning to us the greater angle around, which would be any number that's valued bigger than pi or less than negative 2 pi, then wrap it back around and make it the shorter of the two angles, right? Okay, and yeah, so if it's greater than pi or less than negative 2 pi, then sort it out. Otherwise, just return the regular angle. Let's go ahead and have a look at the example. I think it's this one. Okay, yeah, angle between. Oh, I don't think I have an example. See, I've got delta angle, but that's different. Delta angle is how much. We'll look at delta angle next. We'll leave that for now. Okay, angle between. I don't have an example for angle between. That's all right. Let's quickly make one. Okay, so same thing as before. Let's go to our angle. I'm just going to copy and paste that. And this angle between. If you just joined, I'm sort of working on I'll show you quickly. I've got this website. a very new website that I'm working on, and it's got these examples. I'm just working on cleaning them up a bit, giving them a bit more functionality and making it all a bit nicer. So I'm going to go ahead and add this angle between example. Add this angle between example to this application. Okay, so the first thing I've got to do is make the button. So add to the UI. Okay, we'll create a button. We'll call it angle between. Also create a button. All right. And the next thing I want to do, oh yeah, so I want to add to the index. We're going to go ahead and add a thanks, Truman I appreciate the support. I do appreciate it. I'm hoping to make a fair bit more content, and also I'm curious as to what people are really interested in. I feel like I've been creating things that I know about, and I'm sort of like I got to find that middle point between what people are really interested in watching and what I'm sort of able to work with. So yeah, feel free if you have any suggestions, let me know. Yeah, the portal project was a lot of fun. That was a great one to do. There's a possibility. I don't want to promise anything, but there's a possibility of a revamp of that portal one. Sort of re-look at it, see how we can make it even better. Okay, where are we? Okay, so let's go. I'm just going to add this angle between. Oh, and also I'd be really interested if you have any examples that you made online of like portals or anything like that, or a video of what you made. I'd love it if you send it through. I could have a look at it. Angle between. Okay. Okay, so all I've done now is I've copied our angle example, and now we're able to edit it a bit. So instead of showing this regular old angle, we're going to do an angle between. So we've got to create a pos A, and we'll also have a pos B. Const pos A equals, let's just say the x could equal, I don't know, maybe 100, and the y can equal maybe 150. Okay, and then we're going to rename this to pos B. I'm going to close that off. Okay, so now we'll say const theta, instead of this, this is just a regular old angle. I'm just going to make this angle, make this theta vec2 dot angle between pos A and pos B. Okay, what's going on here? All right, theta equals. Okay, so theta. Okay, now drawing the angle between them will be interesting. We'll get to that later. First of all, I'm going to draw an ellipse for pos A and pos B. Pos A and pos B. Okay, that didn't work. Do a line at pos A and also a line at pos B. Uh-oh. There's a fly in the house. Go away. they usually go away if I just open a window. Let's see how we go. So now we're getting this value, right? Oh, And I've noticed I've written angle between, not signed angle between. I'm just gonna, we'll get to angle between later. Signed angle between. Of course, yeah, no, I won't even touch unsigned angle between. We'll get to that later. But yeah, so you notice we're getting this theta is 0 to negative 0. It's an angle from negative pi to pi. I'll write that in so I don't forget it. Got 2 fixed. 2. Okay. Negative pi. 2 pi. Okay. Okay. So now we're getting these values. So draw the arc. This is probably got more to do with. I want to like draw a little arc so it shows what the angle. Shows which angle is being calculated. We've got to draw an arc from A's angle to B's angle. So we actually need to make a few calculations just so that we're able to draw it. So ignore this if you're. This is only just for drawing the arc. I'm just going to quickly write it in. Const theta A equals vec2 dot angle pos A. Theta B is pos B. Theta B is pos B. And now we're just going to do an arc. Peter arc. And this is going to say if it's a positive angle, then go from A to B this way. Otherwise, go from A to B this way. That's just what this if statement's doing. Okay, so we'll go from theta A, theta B. Otherwise, go from theta B to theta A. See if I got that right. There we go. Lovely. Okay, so now we're sort of getting an angle between. Okay, so that's our signed angle between. Now, we're about to look at unsigned angle between. All that means is you don't get this negative value. So where it says 2.0, 2.1, 2.2, 2.3, it'll be identical on either side. Where is that useful? That's useful in a few different things. It's essentially useful when we don't care about what the angle between them is. If we're just finding out the angle between two vectors because we're talking about, we'll get to some examples where we don't care about it. I won't go into, like, for example, I think these center of circles and next point on circles, they're ones that you need to find out the angle between, but you don't mind whether it's in the front or the side. Oh, here's a good angle between. Okay, so let's say, for example, this is an example from Dan Schiffman's Nature of Code, which is it's kind of where I've learned a lot about this stuff from, especially some of the great simulations that he makes. And one of them he talks about is say this is a little dude, and this is a little dude. Okay, so they're both the same color. I'm just going to change the color of the second one. Okay. So now let's say we got our yellow one is a little guy and our magenta one is a little guy, and the yellow one has vision that he can only see, say, 45 degrees on either side of him, and our magenta one, and we want to find out whether or not he can see this magenta one. Well, completely lost my train of thought. Okay, so where we don't mind whether it's assigned, when we say signed angle between, so it's going from negative to positive. Where we don't mind whether it's negative or positive is where we'll work out, that's when we'll use this regular angle between, which is unsigned. And the way that we figure that out is completely different from how we find out the signed value. Of course, we can just say something like this. Theta equals vec2.signed angle between. This is a cheating way. Theta equals, let's say let for now. Theta equals math.abs theta. Bang, we've lost the sign. I mean, we don't have the sign anymore. That's one way of doing it. But it's not. It's not the right way of doing it. And of course, there's no such thing as right or wrong in code. there are certain cases where you wouldn't want to use this signed angle between and then just taking the absolute value of it. It's worth looking into this angle between, because it will be related to one of the next things we're going to look at. Okay. All right. I've just looked at the board and I've realized there's something I want to talk about before we go into this unsigned angle between, because there's a really good example of where you would use the unsigned angle between. And there's something I want to talk about before we do that. So, sorry, if it's okay with you guys, I'm just going to digress. And we're going to talk about something called a delta angle. And delta angle is essentially the same as angle between, except just